Hello and welcome to the Weights Measures Primer. My name is Ross Anderson. My subject today is what are the risks in testing? And of course, I'm talking about testing verification. To set the stage for this video, I do suggest that you look at some of my earlier videos on related subjects, in particular, what is verification. You may also want to watch what is the verification scale division E and additional thoughts regarding what is the verification scale division E. It turns out as I scripted this video, I had too much material and it would make a very long video, so I've decided to split it. In part one, I want to address asking the right question. I'm sure those of you with some measurement background may have been questioning the word risks. Why am I talking about risks? Normally, with measurement, we talk about uncertainty. Well, I need to explain why risk is the right question. I'll also try to look at the methodology that I'll use to answer that question. I'll begin by talking about two different types of verification. I talked about this in the video, What is Verification? And the first is calibration verification. In this, we use a calibrated standard where we know the quantity and uncertainty of the standard. We know the uncertainty of the test method. And what we do is we compare the reference standard to the instrument under test to determine a difference. In the second step, we take that information and assign a quantity value and uncertainty to the instrument under test. And in step 3, we use that information to make a decision about compliance. Contrast that with testing verification. In this, we start by qualifying the standard. That is, we verify that the standard's quantity value and uncertainty fits within certain rules. Once the standard passes muster, though, you'll see that in the measurement step 2, we use the nominal value of the standard. We use the nominal value to determine a test quantity, which is compared to the instrument indication, and that gives us an error. That's essentially a difference. This error is then used in the decision step. What's critical is that we see that in step 2 and 3 of testing verification, there are no uncertainties. Now, I'm not suggesting for even a remote second that there are no uncertainties in these measurements. Of course there are. What I'm simply saying is it's not part of the equation. I take you back now a number of years to the formation of the U.S. National Working Group on Alternative Test Methods. They were tasked with finding a way to bring new test methods into Handbook 44. I was there at the first meeting. And what they quickly came to a consensus that they needed to find the uncertainties by going out and doing field tests. I challenged them. I said, wait a minute, the existing procedures in Handbook 44 were not validated that way because we don't know the uncertainties of any of the procedures in Handbook 44. So isn't this a double standard? Undeterred, they went forward. They made the measurements in the field. They brought the data back to an uncertainty expert, and what did they find? First, field testing is pretty expensive. And second of all, they learned that the findings were inconclusive. Didn't tell them what they thought it was going to tell them because you can't separate the test variability of the method from the variability of the instruments you're actually testing. And because the variability of the instruments is much larger, you're trying to analyze something way down in the noise. The work group found themselves up a blind alley, and they never recovered. I'm not aware that they ever came forward with the proper recommendations of how would we bring new test methods into Handbook 44. And I suggest that it's because they asked the wrong question. In my video, What is Verification?, I asked a very subtly but significantly different question. I asked if we don't know the uncertainties involved in testing, can we have confidence in the results? I think your initial reaction is to say no, but Weights and Measures has been confident in testing for generations, even before Handbook 44 was written. So has the AOAC, ASTM, IEEE, and OIML. Going back to an earlier slide, we can see that in calibration verification, explicit treatment of uncertainties plays a major role. It's even important in qualifying the standard. However, it's important to see that whether we use implicit or explicit uncertainties, we're talking about measurement results, not compliance decisions. To see what I mean, look at this decision matrix. In the traditional view, we have, coming down from the top, two actual conditions. Things either comply or they don't comply. On the other axis, we have a test method where things either pass or they fail. There are boundaries here between comply and not comply, between test, pass, and fail, and they cross each other at right angles. As a result, we get four outcomes. The upper left, the true positive, and the lower right, the true negatives, are good results. But the other two, particularly the false positives where we pass things that are not compliant, and the false negatives where we fail things that are compliant, those are bad decisions. At issue, though, this diagram is not very representative of weights measures. First of all, this is only 50% compliance. We expect our equipment to be closer to 95% compliant. And our test method we expect to be much better than this, which is no better than a coin toss. So let's redraw the figure. Here's an alternative that might represent a high compliance verification. Notice that we've pushed the non-compliance compliance boundary down into the lower right corner of the figure, and likewise the test pass-failed boundary. But notice that they still cross each other. And the non-compliance here is about 6%, which means that the instruments are 94% compliant. Notice that the number of false negatives and false positives has been greatly reduced. Where it was 25% each in the earlier figure, now you can see it's nearly about 1% each, which means the test effectiveness has gone from 50% effective to about 98. So basically 100% minus the false positives and false negatives. It is the actual number of false positives and false negatives that we're really interested in because that tells us about risk. Uncertainty can't get us there by itself. You have to go beyond uncertainty and integrate uncertainty and the population variability in order to come up with some kind of risk. But I think we can do it another way, and it's called the Monte Carlo method. I'm going to build a Monte Carlo model where we have a verification scale and an instrument scale. And if you remember from my video on the verification scale division E, the verification scale is constant. It's the true value of the standard. The instrument scale is what moves. And the offset between these two scales is the error for that test. Next, we have to measure that offset, and in doing so, we introduce error from both the standard and the test method. And then finally, we have two more things to consider. That is the error from rounding to the verification scale and the error of rounding to the instrument scale. We can simulate the rounding errors using rectangular distributions, and we can simulate the other errors using normal distributions. What's important is to recognize how much of this information we already know. For example, we know the rounding errors because we know the size of the scale division, and the rounding errors are plus or minus a half a scale division. We know the instrument errors from historical data. And finally, we know the error in the standard because those standards are re-verified periodically. And what's left? The test method. What we do in Monte Carlo is basically hold all those values constant and then change the one variable that we want to look at and look at a range of values. Here's a group of instruments I intend to examine with our Monte Carlo model. You'll see there are motor fuel dispensers in gallons and liters, VTM, an LPG meter, and a class 3 scale at the first and second tolerance step. I've also provided some additional information, particularly the units, because the instrument scale and the verification scale are not always in the same units, and the simulator has to all be in one set of units. I've also provided the maintenance tolerance and the standard tolerance, and to show the relationship between the standard tolerance and the maintenance tolerance of the instrument. Next, I'll add two more columns for SR and ER, meaning the starting resolution and the ending resolution. And I think these two need a little explanation. In this table, I'm going to walk you through two different types of calculations for instrument error and show how it's done in the simulator. So with the motor fuel dispenser in the center column, we are going to work this in cubic inches. And the first thing the simulator does is it picks an instrument error for this test. This case, minus 6.438 cubic inches, which does not comply. We then start on the instrument scale. We stop the test at 5 gallons, which in cubic inches is 1155. But we must recognize that there's some rounding error here because that's a rounded off value. So we pick a rounding error within plus or minus a half of one scale division. We then pick a test error plus 0.637 cubic inches. And we add those first four values together and we get 1149.252. And what is this? This is what the inspector would see in the sight tube. And this value is constrained by the other four values. And so this is not fully allowed to vary the way the other ones are. The 1149 minus 1155 gives us a minus 6 cubic inch result, which passes the test. But what we've done is we've passed a non-compliant instrument. When we move to the class 3 scale, we again start by picking the instrument error plus 0.946E. That complies. And our start reading is 500E on the verification scale. Next, we see that there is no rounding error. There is no rounding error from the start position because we used an artifact that's at the exact center of the scale division. Now we add in the test error, 0.158E. Add that all together, we get 501.104. Now what we're going to do is round that off to 0.2 on the instrument scale, which is 501.2 based on R76. 501.2 minus 500 gives us an error of 1.2, which fails the test, but that was in fact a compliant instrument. For comparison purposes, I've added two more columns, comparing the starting resolution to the maintenance tolerance and the ending resolution to the maintenance tolerance. My purpose here is to highlight those cases where the rounding may be an issue. So on the start resolution, we see the VTM is an issue because the rounding is to 1/3 of the maintenance tolerance. That's one scale division. For the ending resolution, we see the motor fuel device is either 1/6 or 1/5 of the maintenance tolerance. And for the class 3 scale, it's either equal to the maintenance tolerance or half of the maintenance tolerance. And the other thing that stands out is the LP has sufficient resolution on both starting and ending resolution. This brings to a close part 1 of my video on what are the risks in testing. I've tried to show that uncertainty is not really what we're after. We need to know false positives and false negatives, decision errors, and that comes down to risk. And I've devised a tool, the Monte Carlo tool, to allow us to examine that. So imagine that now I'm going to go crunch those numbers in my simulator, and what I'll come back in part 2 is come back and evaluate the results that we get. Thank you so much for watching. Please come back and visit part 2.